Alrighty, gang, welcome here. I apologize, I know I posted that link just a few seconds ago, so I'll give you guys a second or two to trickle in. My last class went a bit over time. Today we're going to talk about average rates of change, which is one of the more important sections with regards to preparing you for Calc 1. So it's a section through which we're going to move very carefully. And I want you to please ask questions along the way if you haven't. I imagine you will. So we're going to take our time here today. That's all right. Okay. Now let me flip on the document camera. I'm going to talk a little bit about homework and quiz structure over the next few days. And it's MAC1140, section 009, which is a pre-calculus class. Today is the 7th of September, 2021. And on the docket for today is average rates of change, which I will, as often as I can, abbreviate as AROC, because it takes a while to write. And this is section 2.4. Some announcement-y things. Homework 3 is due right now. So if you didn't get that done over the weekend, it was a pretty short homework, but I know there was the holiday. If you didn't get this done, please submit an extension request in WebAssign and I'll grant it. You need to hurry up and finish that. Some new stuff coming out. Homework 4 will come out today. And will be due Thursday at the start of class, as always. And then there's also going to be a quiz. Quiz 1 comes out this week. I'll try to get it out for you today. My afternoon's a little bit busy today. I may not have time. This will be due next Tuesday. At the start of class, as always. All right. I want to talk a little bit about rules for the quiz because it's in WebAssign. It's not proctored, but it is treated as a graded assignment. So here's what that means. Since this is an assignment that is graded for correctness and you have a limited number of attempts, I'll talk about that in just a sec. You're not allowed to use outside resources for the quiz. The way it works, you'll have 3 attempts for each problem on the quiz. And my suggestion is use the 3 attempts per problem to do 3 runs of the quiz. So rather than going through and solving the first problem 2 or 3 times to get it right, and then moving to the next problem, proceeding like that, I suggest you treat it like a test. So sit down, do the quiz, enter your answers, see which ones you got right, see which ones you got wrong. Then those ones you got wrong, bring them to me, bring them to office hours. You can bring them to a tutor, you can talk about them in the Discord. But you need to tell the tutor if you're going to bring it to a tutor, or you need to tell the Discord if you're going to ask about it in the Discord, this is a quiz problem. Do not ask for help while you're taking the quiz. All right, solve the problem, see which ones you get right, see which ones you get wrong. The ones you get wrong, you can then ask for help with. But then when you retake the quiz and you run through with your second attempt, you need to make sure that you're solving those problems on your own. Treat it like it's practice for the test and it will serve you well. Treat it like it's just something you're doing for a grade and it'll feel like a busy work and a waste of time, and it will be. But if you approach this with the right attitude, then it can be a really helpful tool getting you ready for the test. Again, three attempts altogether for the quiz. No time limit or proctoring mechanism, but I want to urge you to be smart about this. And being smart about this means using the tools you have to prepare yourself for it. Okay, that's all the announcement-y stuff. Let's get into the meat. So average rates of change. This is section 2.4. Average rates of change. I'm going to try to introduce this concept by talking about a very concrete example. Imagine at time x equals 0, I get in my car and drive north. So I'm driving along a straight line. I'm just going to go straight north. Pretend it's some sort of idealized world where I've got a road outside my house that just goes north forever. And the function f of x outputs, so the function f, I should say, outputs when you feed it the input x, the distance I am from my home. Maybe distance in miles. Okay. Say we'll measure time in hours and distance in miles. This function f of x, this is called a displacement function or a distance function. Physicists would call it a displacement function. When x is equal to 0, 0 hours after I've left, that's the moment I'm leaving. So f of 0 has to be 0, right? Because at time x equals 0, I'm getting in my car and leaving. If 1 hour later, I am 40 miles away, then f of 1 would be 40. Do we feel like we understand what this function does? If I turn around and come home, and I get home 5 hours after I leave, then f of 5 would be what? Show me that you're thinking along with me. So if I turn around and come back home, and 5 hours after I leave, I arrive back home, what is f of 5?
0.
0, right? Because I am 0 miles from my house. If I arrive back home, my distance from my home is 0. Okay. I'm going to draw for you a little graph here. This will be the graph y equals f of x. This is in miles. And this is my time, and it's in hours. Okay. And then here's 1 hour, 2 hours, 3 hours, 4 hours. So would have an this, right? Let's do it like we said. Let's say I arrive back home 5 hours later. I want you to think about what this graph describes. The y values are how far I am from home, and the x values are how long since I left. So 4 hours after I leave, I am 40 miles from home. 1 hour after I leave, I am 20 miles from home. 2 hours after I leave, I am 60 miles from home. Do we understand this graph? All right. What I want to ask is, what's the question? Can I get any speed information from this graph? Right, so I'm on a journey. At any moment in my car, I can look down at my speedometer and say, oh, I'm going 35 miles an hour. Oh, I'm going 70 miles an hour. If you're not in the car with me for this journey, obviously you can't look over at my speedometer, but maybe you do have this graph. Can you figure out how fast I'm going at any time? Can you get any information about speed from the graph whose vertical axis is distance and horizontal axis is time? Answer: speed, or more accurately, velocity, has units of distance over time. For example, um, 10 miles per hour, that's the same as saying 10 miles over 1 hour. The word per means divide. Think about the word percent. Right? Anybody taking Latin or French? Cent, 100. Percent means out of 100 or divided by 100. So when I say I'm going 10 miles per hour, that means I traveled 10 miles over 1 hour. It's a distance divided by a time. So over here, if I take some non-zero distance and some non-zero time interval, for example, from time 0 to time 1, I could ask, what's my average speed over that first hour? Okay, so here we go. What is my average speed from x equals 0 hours to x equals 1 hour? In other words, what's my average speed over the first hour of this journey? Well, you take the distance I covered. So over that first hour, I went from being 0 miles from my home to being 20 miles from my home. And then you divide it by the time it took me to travel that. So this would be the distance covered from x equals 0 to x equals 1 divided by the time elapsed from x equals 0 to x equals 1. Now remember that denominator, the x's are the time. So the bottom's easier. How much time has elapsed from hour 0 to hour 1? Genuinely asking.
1 hour.
1 hour. Yeah, 1 hour has passed. So downstairs here, this is 1 hour. Upstairs, how much distance have I covered from 0 to 1, from x equals 0 to x equals 1? Well, I've covered 20 miles. I started 0 miles from home, and at the end of that time interval, I'm 20 miles from home. So my average speed is 20 miles per hour. And we won't usually write the word per, we'll usually write the algebra of the units, which is miles over hours. If you've taken any physics or chemistry, you've heard about dimensional analysis before, where you kind of do algebra with units. We'll be doing plenty of that in this section. All right. So what did we do? I took the difference in y values and I divided it by the difference in x values. I took this x value minus this x value, put that downstairs, and I took this y value minus this y value, and I put that upstairs. You've seen this before. What is this? In terms of the geometry of the graph, what is this? Yeah, it's a slope. It's a difference of y values divided by a difference of x values. That's a slope. So we're going to return to this graph in just a second. Let's go ahead and do it now. No, I take that back. I'm going to define the thing, and then we're going to return to this. So here we go. Definition. The average rate of change for the function f from x equals a to x equals b is f of b minus f of a over b minus a. And this is a slope. We're going to talk about interpreting this as a slope, but the first things I need to tell you are that you got to get used to this notation. No y2 minus y1 over x2 minus x1 stuff. Got to get used to the function notation. Remember last week I was saying like we have to gatekeep function notation in this class. I cannot promote you through this class unless you demonstrate that you are comfortable with function notation. This is one of those places, talking about average rate of change, where this is a big fucking deal. So please work in this notation. I'll show you lots of examples. The geometric interpretation here is a slope. It's a slope not of the graph though, right? This graph, look, it's curvy here. It doesn't have one slope. It's steeper over here than it is over here. So it's the slope, but it's the slope of something else, not the black graph here. And I'll tell you what it's the slope of in just a second. But before we do that, I want to tell you one other thing. Average velocity is equal to the average rate of change of the position. And remember here, velocity is speed with direction. So a velocity is technically a vector, which means it's got a magnitude and a direction, if you like. But velocity and speed are almost interchangeable. In common parlance, we use them interchangeably. But the truth is that velocity can be positive or negative. If you're going in the positive direction, then your velocity is positive. If you're coming back, then your velocity is negative. So average velocity is the average rate of change of position. And what is velocity? Well, velocity is basically speed But if it's positive, you're going one direction. If it's negative, you're going the other direction. Leave space down here. I'm going to come in and draw some pictures for you. I want those pictures to be close to the definition of the average rate of change in your notes. And then for now, come back over here and let's answer some other questions. All right, let's do this. So I'd like to find the average speed from 0 hours to 3 hours. So over those first 3 hours of the trip, what's my average speed? Well, I'm going to take the distance divided by the time. And I know that this is the same thing as the average rate of change from x equals 0 to x equals 3. Same thing. What is it? Well, over those first 3 hours, I've gone a total of 60 miles. All right, 3 hours after I leave, I am 60 miles from home. So this is going to be 60 divided by the amount of time it took me, which is 3. Now 60 divided by 3, that's 20. The numerator is miles, the denominator is hours, so this is miles per hour. So in other words, over the first 3 hours of this trip, I averaged 20 miles an hour. Going kind of slow. What about the average velocity from the second hour to the 5th hour? Here I'm looking for the average rate of change from x equals 2 to x equals 5. So now I'm not saying starting at 0, I'm saying starting at 2. What's my average velocity from here to here? This would be the y value here, which is 60, minus the y value here, which is 0, divided by, oh no, I'm sorry. So let me write this in the correct notation, the full notation. This is always a bit like this. This is f of 5 minus f of 2 over 5 minus 2. All right, that's our average rate of change from 2 to 5. F of 5 is 0. F of 2 is 60. You see what I did? I was doing the subtraction in the wrong order up there. And then 5 minus 2 is 3. So here we're going to get negative 60 over 3, or negative 20. And the units are still miles per hour. So why is my velocity negative from 2 to 5 and positive from 0 to 3? What does that even mean? Can somebody explain?
It's positive when you're leaving from your house. And then when you're going back to the initial location, you're going quote unquote backwards.
Very good. Yeah, exactly. Remember, velocity encodes direction. So a positive direction or positive velocity means I'm moving in the positive direction, or in this case, away, because I'm starting going away from my house. And a negative velocity means I'm moving backwards along that same path. Okay. So what's the geometry here? If we're finding a slope, what are we finding the slope of? Let's look at the 0 to 3. Let's look at this guy. If you want to think of this as a rise over a run, as a slope, then the 2 points that are being connected there are these 2 points. So the slope you're finding is not the slope of the graph. It's not the slope of the black function. It's the slope of this blue line. And in part C, we were finding the slope from here to here. And you see that line, that has a negative slope, right? He's going down overall. So let's return to the maximally general picture, the definition. And I'm going to tell you the names of these lines. These have a special name. This is a note. And here's the nice general picture. You have a arbitrary function, generic function. Perhaps something like this. And you want to find the average rate of change over some interval, like from x equals a to x equals b. The thing that you're finding there is the slope of the line that connects those 2 points. And that has a name. Does anybody know the name for a line like this that connects 2 points on a graph? I'll just draw it in solid. It's a different color, right? If you're working in one color, I recommend dotting this line. Remember, the point here is a comma f of a, and the point here is b comma f of b. So f of b minus f of a, that's this y value minus that y value over b minus a, that's a rise over a run. This is the slope of the secant line. And I know some of you are taking trigonometry right now or have taken it in a previous semester. The secant line is intimately connected to the secant function from trigonometry. The secant function outputs the length of a certain secant line. When you think about things in terms of the unit circle, you put your unit circle centered at 0, 0 in the xy plane, and you look at where that the line that that comes up to the terminal point on the circle intersects the x-axis. That's a secant line. But that term in trigonometry comes from this more general term. So a secant line is a line that connects 2 points on the graph. And the slope of that secant line is the average rate of change for this function from x equals a to x equals b. And sometimes instead of saying from x equals a to x equals b, I'll say over the interval a to b, and that means the same thing. Really what we're asking is, how much has your y value changed over this interval? And that's something we've heard before, right? Where else have you heard that? how much has our y value changed over this interval? In other words, where have you seen this numerator before? Back to last week.
The net. Or
Yeah, this is the net change. I'll put this in purple. This is the net change over the length of the interval. So the average rate of change is the net change divided by the kind of length of the input interval you needed to achieve that net change. And it happens to be a rise over a run. It happens to be a slope. Okay. So let's look at a specific example outside the world of physics. Just a straight up math problem. Let's find the average rate of change. I'll abbreviate that as AROC. Find the average rate of change for f of x equals x minus 3 squared from x equals 1 to x equals 3, and from x equals 4 to x equals 7. And I think it's also a wise thing to do here to look at the graph of this function. So let me sketch the graph right here, and then we'll do the work down below. All right. 1, 2, 3, 4, 5, 6, 7. And then all this 9. Something like this. I'll try a new one. Okay. So here's the function f of x equals x minus 3 quantity squared. You should remember how to graph something like this from previous algebra classes. If you don't, I'll teach you later, but it's the same as x squared. It's just shifted to the right by 3 units. So some points that we're going to be messing with. 1 comma f of 1 is important. 3 comma 0 is important. 4, I'm not too sure what the y value here is at 4, but that's okay. And I know 7, it's going to be way up there. I won't draw it. Too big. So for part A, the average rate of change is f of b minus f of a over b minus a. That's the definition. This is anytime I ask you for an average rate of change, your first thought should be this. This is the definition of the average rate of change. It's the net change divided by the length of the interval. F of b minus f of a divided by b minus a. And remember, these objects in the top, f of b and f of a, those are function outputs. This is function notation. There is no multiplication going on upstairs. That's not f times b, that's not f times a, that's f of b, and that's f of a, which means there's nothing you can cancel or factor or clean up here. I can't cancel the b's, I can't cancel the a's, nothing like that. All we can do with this is plug into it, that's it. Maybe after we plug in, there will be some nice things that we can cancel, but for now we can't. Here, A is 1 and B is 3. B is always the bigger number, always the larger input. We always go from A to B. So this is f of 3 minus f of 1 divided by 3 minus 1. Is everybody with me so far?
Yes.
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 Wonderful. All right. I could at this step come off to the side and figure out what f of 3 is. And I could also off to the side figure out what f of 1 is. But instead of doing either of those, here's what I'm going to do. I'm going to just plug in what is f of 3? Well, it's 3 minus 3 all squared because f of x is x minus 3 all squared. This big minus is this minus. This minus is this minus. And then what is f of 1? F of 1 is what I get when I plug in 1 here. So that's 1 minus 3 all squared. And then downstairs, we just have 3 minus 1, that's 2. Choosing to do the workflow in this way is smart on these simpler problems, because on the more complex problems, you'll have to do it this way. And this is kind of warming you up for that. I know the expression on the far right looks a little complicated, but if you take your time and practice your order of operations, you can manage shit like this, and you'll have to manage shit like this. So let's do it. I've got these parentheses here, and they have powers, which means I have to handle the stuff inside the parentheses first. So 3 minus 3, that's 0. So this is 0 squared minus 1 minus 3 is negative 2. So that's minus negative 2 squared, all over positive 2. So what do I get? Well, 0 squared is 0. Negative 2 squared is positive 4. 0 minus 4 over 2, or just negative 4 over 2, or negative 2. And here, what that means geometrically is that the slope of the line, the straight line that connects these 2 points along my graph, this little purple line that I've just added in here, has slope negative 2. Doesn't mean that the graph has slope negative 2. The black graph doesn't have any fixed slope. His slope is changing, right? Like over here, he's kind of shallow, but over here, he's really steep. So I can't talk about a slope for the black graph, but I can talk about the slope of the purple line connecting any 2 points along that black graph. And that's the purple line is called the secant line. All right, that's it for part A. Are there any questions on what we've done here or what that means in terms of the picture? Okay, let's do part B. Here, my average rate of change is going to be always f of b minus f of a over b minus a. And never can we do anything at that step. We've got to plug in. So this is f of 7 minus f of 4 over 7 minus 4. All right, a here is 4, b here is 7. What is f of 7? Well, I know f of x is parentheses x minus 3 squared, so f of 7 is parentheses 7 minus 3 squared. This minus comes from the formula. And then f of 4 is 4 minus 3 squared. And all of that is divided by 7 minus 4, which on a good day is 3. Now 7 minus 3, again, just like before, we got to follow our order of operations, work out the shit inside the parentheses. 7 minus 3, it's 4. So 7 minus 3 squared is 4 squared. Minus 4 minus 3 is 1. So this piece is 1 squared. And still dividing by 3. And then continuing to follow your order of operations, you got to deal with the powers. 4 squared is 16 minus 1 squared is 1. So this is 16 minus 1 over 3, which is 15 thirds or positive 5. And this guy, I don't have room in my picture, but this guy would be the slope from this point to the point above 7 here, which would be like way up off my screen there. You see that that's definitely a positive slope, right? That line would look like this, and it's going up as we go to the right. That's a positive slope.
I'm sorry, I actually am kind of confused as to how you get the second number whenever you expand like f of 7 and then f of 9. Where are you getting 7 minus 3 and 4 minus 3? Is it to like make it 0? I don't.
No, so look at the definition of the function f of x.
Okay. Oh.
So let me come in.
Okay, so you just okay, I understand.
Yeah,
All right.
no worries. So this is f of 7. This piece right here would be f of 4. Similarly, this piece right here is f of 3. And this piece right here is f of 1. The reason I'm writing it like this, instead of going off to the side and finding f of 3 and then just plugging that in, is because later we're going to look at more abstract inputs. Instead of saying from 1 to 3, I'm going to say from a to a plus h. And then we have to write it out like this. So it's good to get in that habit now. Okay, one fun game I can play, I could ask you to find the equation of the secant line. Does anybody remember how to do that? Bonus challenge. Find the equation of the secant line to f of x from x equals 1 to x equals 3. Let's find the equation of that secant line we drew. We already know the slope. What's the slope of that secant line?
-2.
Yeah, it's the average rate of change, which is -2. What other information besides the slope do you need to find the equation of a straight line?
The y-intercept?
That would be sufficient. If I knew the y-intercept, I could say, okay, it's mx plus b, where b is that y-intercept. But I don't know the y-intercept. Is there any other way we can get there?
Theoretically, I would just follow the slope and like extend the line, but I assume there's like a more mathematical way.
Yeah, good answer, Gavin. So yes, you could. You can take a point that you know on the graph and kind of try to walk it over, you know, incrementing by the appropriate amount due to the slope to get your y-intercept. But there's a much better way to do this. All you really need is a slope and a point. Because y equals mx plus b is a special case of the point slope formula. So here, a point that I know is on the graph, I could say 1 comma whatever. What is f of 1? It's 2 or something. 4. But here's an easier one. I know 3 comma 0 is on the graph. So these things together with the point slope form of a line, which is something you will need in this class and certainly in calculus class. It says you can take any point x1 comma y1 that's on your graph, any point on the line. So yeah, the y-intercept is nice. The y-intercept is the point 0 comma b. So if you plug in 0 for x1 here and b for y1 here, you get y minus b equals mx, which is y equals mx plus b. It's a special case of this. This works for any point on the line. So I'm gonna be lazy. I'm gonna use this point, which I already have both coordinates of. And then I just plug everything into this point slope formula. So here, x1 is 3, y1 is 0, and I get y minus 0 equals -2 times x minus 3. Which, y minus 0, that's just y. And if you distribute the -2, you get -2x plus 6. And that's it. That's the slope of that's the equation of that secant line. And I'll tell you right now, this sort of question makes a very good exam question. Like, here's a function. Find me the equation of the secant line from x equals 2 to x equals 4. You would need to find the average rate of change for that function. That average rate of change will be the slope of your secant line. And then you'd use your point slope formula or y equals mx plus b to find the equation there. But the big thing that we're worrying about today is just the concept of an average rate of change. So I'll pause here. This is kind of our easy example to get us comfy with the concepts. Are there any questions about what's going on before the bonus part? Make sure we're all rock solid comfy here. Take whatever time we need. Make sure your notes are nice and pretty. Remember, everything I put on the dot cam needs to go in your notes. Okay. Let's look then at a slightly more complicated example. And stuff here. So at time t equals 0, I drop the pre-calc book off a cliff. All right, I'm fed up with it. Just done. Throw this thing off the cliff or drop it off the cliff. It is a fact of physics that the distance the book has fallen ignoring wind resistance, the distance the book has fallen t seconds later is given by, I'll call the function d of t. It's 16 t squared. And that's measured in feet. So if I want to know how far has the book fallen after 1 second, I'd plug in t equals 1 here, 16 feet. If I don't know how far the book has fallen after 2 seconds, I plug in t equals 2 here. I get 16 times 4 is 64 feet. Does everybody understand what this function's doing? Just tells me how far the thing has fallen. I'd like us to do 2 things with this. I'd like to find the average speed of the book from t equals 1 second 2t equals, let's keep it reasonable, 5 seconds. So this book is going to fall for a while. Maybe it's like the Grand Canyon or something. I want to know from second 1 to second 5, how fast was I going on average?
I'm sorry, where does the 16 in the equation come from? Is it like the amount of seconds it took to hit the ground, or like?
No, it's something else.
Yeah, that's
This describes free fall close to the surface of the Earth. So the Earth has a certain mass. That mass, according to Newton's laws, forces to exert a certain force on any nearby object. That's law of gravitation. And if you plug in the mass of the Earth and all the other statistics into Newton's equations, you'll find that close to the surface of the Earth, the acceleration due to gravity is about 16 feet per second per second. So you gain 16 feet per second in your velocity every second you go by, or in SI units, it's about 9.8 meters per second squared. So 16 comes from gravity.
okay.
Yeah.
Thank you. That clears things up. I was like, well, how is this? I don't understand.
Yeah, on Mars, this would be a little bit smaller. And on Jupiter, this would be a lot bigger.
That's actually surprising because that seems really strong and people survive like falling out of planes somehow.
It is really
It's
strong.
kind
So
of crazy.
remember what I said, this is realistic as long as you ignore wind resistance. Wind resistance is a very big deal for describing terminal velocity. So this book wouldn't keep accelerating like that forever. It would eventually reach its terminal velocity, which is governed by things like its surface area. But if we assume, atmosphere free, I suck all the air out of the Earth, then it would fall exactly like this. And it's a good approximation for small objects. All right, let's do the thing. How do I find the average speed? What am I looking for here?
The slope between those 2 points.
Sure, but I don't have a graph, right? I could draw a graph of this and then we could try to interpret it as a slope. But let's try to interpret it as a rate of change. So the average speed should be the average rate of change for the distance, right? Distance over time. So what I'm looking for here, we could interpret it as a slope, that's correct. But I'm looking for the average rate of change in the function d of t from t equals 1 second to t equals 5 seconds. So what is that? Well, according to my formula, remember f of b minus f of a divided by b minus a. Here, the only difference is my function has a different name. It's not called f, it's called d. So this would be d of 5 minus d of 1, which is the net change from t equals 1 to t equals 5, divided by 5 minus 1. How far did it fall? Divided by how long was it falling? From 1 to 5 seconds, it's falling for 4 seconds. The downstairs here is 4. That's how long it had to fall. How far did it fall over that time? Well, that's the difference in the outputs for this function. And again, remember, function notation cannot factor out a d, cannot cancel the 5 or the 1 or any shit like that. The only thing we can do with this and this is plug in here. So d of 5 is 16 times 5 squared minus, coming from the formula, d of 1 is 16 times 1 squared. And our first thought when we look at something like this is, my God, the arithmetic. But algebra will save the day. 5 squared is 25. I don't want to compute 16 times 25 though, because I'm lazy. So here's what we do. First, follow your order of operations. This is 16 times 25 minus 16 times 1, because 5 squared is 25 and 1 squared is 1, all over 4. But now when you look at the top, do you see anything I can do with that 16? I've got one term here I've got another term here, and 16 shows up in both. So what can I do with this 16 that saves me from having to do this multiplication?
16 minus 16.
I can't do 16 minus 16 because this one's attached to a 25 and this one's attached to a 1. 16 minus 16 would be 0, but I can factor a 16 out. And then when I factor that 16 out, I have left 25 minus 1. And all of this is still over 4. So there's a common factor of 16 in these two terms that I can bring out. And then 25 minus 1, that's not hard. That's 24. So this is 16 times 24 all over 4. And then 16, that's 4 times 4. So you can cancel now. Remember the rule, you can cancel if and only if you can factor. 16 over 4 is 4. So this is 4 times 20 times 24, which is 80 plus 16 is 96. So I'm saying 16 is 4 times 4. So this numerator is 4 times 4 times 24. 4 times 4 times 24, all divided by 4. You can cancel one of those 4s. Kind of rule here is just like A times B over A. You cancel the A's and you just get B. So 4 times 4 times 24, all divided by 4. You can cancel one of the 4s and you just get 4 times 24. So everybody see what's going on there? Kind of two big things, right? The function notation to get us from here to here correctly. Without that, we're dead in the water. And then just the algebra skills to help us simplify this nicely. If you had to blow all this apart, you would want to use a calculator, right? But we're not going to have a calculator on the test. Or certainly, you don't need a calculator. The only calculator you're allowed to have is one for basic arithmetic. You want to get to a place where you can manage these things without panic. And it's not bad, right? No step of this was bad, as long as we approach it with some intelligence. What does this mean? The fact that this came out to 96. 96 what? And what is it telling us?
Isn't it 96 feet per second?
Very good. So the top here is measuring distance in feet. And the bottom here is measuring time in seconds. So this is 96 feet per second. That's pretty fast. It's not super fast, but it's pretty fast. Feet per second is a weird set of units. If you've ever played paintball, I think they usually limit you to like 300 feet per second. So this is about a third as fast as a fast paintball. That's pretty quick. Was the book going 96 feet per second that whole time?
No, it's just the average of it.
Very good. So at time t equals 1 second, it was definitely going less than 96 feet per second. When you drop something, it goes faster and faster and faster and faster as it falls. So at time t equals 1, it was going less than this. And at time t equals 5, it was probably going much more than this. This is the average speed over that time interval. Now there's a neat fact, and you'll learn this in calculus. There was, for sure, one moment between 1 second and 5 seconds where the book was going exactly this fast, but just one moment. All right, I have a part B to this. We're going to find a formula for the average speed. from some generic time, let's say from some generic time t equals a to some time slightly later, which I'll call t equals a plus h. All right, so a plus h is a little bit bigger than a. So we're saying from some time to some time a little bit later, but we're letting all of that be generic. The time that you're starting and the time separating the start and stop are both variables here, or parameters. Calculations like this, an average speed over a generic small interval, are where Calc 1 really gets exciting. Right? You start looking at expressions like this, the formula for the average speed over a generic interval like that, and you start shrinking that interval down. And that's what's going to get you to the concept of instantaneous velocity. How fast is the book going at this moment? You would take the object we're going to calculate here and then send h to 0. That's called the derivative, but that you will learn in calculus. Right now, what I need you to do is learn the algebra necessary to find such a formula. And it's going to start by writing down the average rate of change formula. So here what we're looking for is the average rate of change in the distance function d of t from time t equals a to time t equals a plus h. This is going to be a little messy. It's going to have some extra symbols in it. But we can follow the exact same sequence of steps we followed here to arrive at a pretty nice answer. By definition, this is d of a plus h minus d of a all over a plus h minus a, right? A is a, b is a plus h. Remember your first homework set, second homework set, last week's homework, where you had to compute things like this, f of a plus h, f of x plus a, that sort of shit. This, just like here, there's nothing we can factor, cancel, clean up, blah, blah, blah. Nothing we can factor, cancel, clean up, blah, blah, blah. You just got to plug in for this thing, and you got to plug in for this thing, and then try to work it out. I'll add a little note here. This was the crux of part of last week's homework. D of a plus h is not the same as d of a plus h. You cannot just tack an h on the outside. And it's very much not the same as d of a plus d of h. None of this shit works. You just have to plug in. So what happens if we just plug in? Well, d of t is 16t squared. So if you plug in here a plus h, that means you have 16 times a plus h all squared. So there is d of a plus h. Minus d of a. Well, again, d of t is 16t squared. So d of a is 16a squared. And then downstairs, that we can clean up a little bit. This is just a plus h minus a, like 2 plus h minus 2 is just h. This is that thing that was called the difference quotient in your homework. All right, how do I simplify this difference quotient? Somebody help me. What can I do with this mess?
Factor out the 16.
Very good. Just like we did before, there's a common factor of 16. Let's bring that guy out. He has no place in there. All the other stuff is A's and H's. So there he goes, factored out the 16. that first piece, when I factor out the 16, just becomes a plus h squared. This second piece, when I factor out the 16, just becomes a squared, and the minus stays a minus. Now, in the last guy, I could do, 16 over 4 and cancel that up, but 16 over h, there's no obvious way to cancel 16 with an h because I don't know what h is. So there's nothing like that I can do. I'm going to have to clean this up. What's my first step in cleaning up something like this? Specifically, what do I do with this?
Is it FOIL when you multiply it? Okay.
Yes, yes, exactly. I've got a sum of two terms being raised to a power. So it's not just a squared plus h squared, you got a FOIL. So I'll say here, a plus h all squared. If you know how to do this quickly in your head, that's great. If you don't, here's how you do it. This is a squared plus ah plus ha is 2ah plus h squared. So that's 16 bracket a squared plus 2ah plus h squared minus a squared all over h. So remember, powers don't play nice with addition or subtraction, ever. The same reason roots don't play nice with addition or subtraction. You got to FOIL. There are tricks for this sort of shit, right? If you want fast tricks for this, look up Pascal's triangle and the binomial theorem. We'll talk, it's a topic at the end of the course, but it's worth self-studying a little bit at the start, I think, if you're the sort of person who hates spending time FOILing. All right. What can I do with this? Does anybody see anything nice here?
A squared goes away.
Yeah, I've got positive a squared here, minus a squared there. These go. They're not canceling like the 16 and the 4 cancel, they just add up to 0. And what's left? Well, I've got 16 times bracket 2ah plus h squared, and all of that is being divided by h. Now let me pause for a second and tell you the goal. Remember I said in Calc 1, you're going to be forming difference quotients like these with the intention of sending h to 0, bringing those 2 points close to each other. So the challenge is that there's an h in the downstairs. You can't send h to 0 as long as there's an h in the downstairs. You can't divide by 0. So the goal, when you're given a problem like this, say, difference quotient, simplify as much as you can, your goal is to always get rid of the h in the bottom. With that in mind, what can we do here?
Can we factor out an h? Okay, cool.
Good, yeah. So the only way I can get rid of something like this is to cancel it. In order to cancel it, I need to have a common factor top to bottom of h. It looks like maybe there's a factor of h here. The only way to be sure is to factor it out. So if we can factor out an h, then and only then can I cancel it with the h in the bottom. And lo and behold, 2ah plus h squared, if I try to factor an h, the 2ah becomes 2a. The plus h squared just becomes plus h. So I have 16h times 2a plus h all over h. And now I can cancel. Just get 16 times 2a plus h. And this would be a perfectly acceptable answer. If you want to distribute the 16 and call it 32a plus 16h, you can. But I would be very happy with this. I'm going to pause for a minute, and then I'm going to kind of preach a little bit about the important steps here. So first, a quick pause, check your notes. Any questions? Okay, here's the critical steps are here. You got to know what you're computing. You got to know that you're after an average rate of change. So you need to know that the average speed is always the average rate of change of distance or displacement. Speed is how far have you gone over how long did it take you to go there. Then you need to be comfortable going from this expression to this expression. That's probably the most important step. Knowing that d of a plus h is just what you get by taking d of t and plugging in a plus h. Knowing that you cannot do any of this stuff. This is not allowed. If you were to write this as 16a squared plus h on the outside, that's wrong. It's not the same thing as this. And that's what the homework last week was meant to highlight, where you had to calculate f of 1 minus x, or f of 1 over x, or f of a plus h, right? We saw these things there. This is why. From there, it's stuff that in theory, we all know how to do from previous algebra classes. We're factoring, we're foiling, we're cleaning up, we're factoring again and canceling. But these are steps that you need to practice. And if you're feeling at all uncomfortable with any of them, please come talk to me. I've got lots of resources for you. All right. How am I doing on time? Still doing good? I'm moving a little quick here, right? Oh no, 12:30 to 1:45, is that the class? It is. All right. Let me, in parting, say one little thing. Let's come back to this. If I calculated the average rate of change, we're coming back to this function now, from 0 to 3, or 1 to 3, which we did, 2 to 3, even like 1/2 to 3, or -1 to 3, all of those would be negative, right? Because this point stays here, and those points over here are all above that point. So that secant line would have a negative slope. If I calculated the rate of change from 3 to 4, or 3 to 5, or 3 to 7, all of those would be positive. And you notice that this function is decreasing everywhere here. Decreasing everywhere here, and increasing everywhere here. So there is a connection between average rate of change being positive and your function increasing. There is a connection between your average rate of change being negative, like it is here, and your function decreasing. But that connection can be very, very, very subtle. For example, so I'll just draw this picture and then I'll let you guys go. So average rate of change and increasing / decreasing. If you know your function is decreasing everywhere on the interval a to b, then you can be confident that your average rate of change will be negative. And conversely, you know your function is increasing on the interval AB, then you can be confident that the average rate of change will be positive. That is true. That is true. But is the converse true? If you know the average rate of change is positive, can you conclude that the function was increasing? Or if you know that the average rate of change is negative, can you conclude that the function had to have been decreasing? And to answer that question, so here, question. What about the converse? Does a positive average rate of change imply increasing? Or does, the other one, does negative rate of change, negative average rate of change imply decreasing? I'd like you to think about that question because its answer is not entirely obvious. It kind of depends on how far apart A and B are. But it's a good question for you to ponder as we move out of today's lecture and into Thursday's material, which is what we're going to be doing next time. So that's all I have to say about rates of change, average rates of change at least. The difference quotient is going to be a big deal in this section. You're going to have plenty of homework problems that ask you to compute things like that last part B from our final example there. And you need to really practice the algebra of the function notation. The other thing you need to do is get in your head the relationships between the graphs and the rates of change. Remember that curvy graphs don't have a slope, right? This function right here does not have a slope. The dotted line has a slope, right? The slope on the curvy function is always changing. That's what makes it curvy. So we can't talk about the slope of this function at a point, not without calculus. And then the average rate of change is the slope of the secant line. I'm going to leave it here for today. If there's anything you guys need to talk about, you can come see me in office hours, send me a Canvas message or an email. I'm still getting through a backlog of those from the weekend, but I am responding to them. If you need to see me more urgently, you can come by my office hour, which is tomorrow from 1 to 2 p.m. And that's it. Be on the lookout. There's going to be a new homework dropping today. That's going to be due Thursday at the start of class. There's going to be a quiz dropping either today or tomorrow that will be due next Tuesday at the start of class. Alrighty, I'll see you guys on Thursday.